Welcome to Keentel Engineering. Standard reliability indices are built to measure the grid on its ordinary days. They are deliberately designed to exclude the worst days, the hurricane, the ice storm, the cascading failure. That exclusion is intentional. It keeps year-over-year comparisons fair, but it also means that the events that matter most to communities, regulators, and large load owners are exactly what those headline numbers hide. Resilience metrics are built for precisely those days. In this video, we walk through the blind spot in standard reliability indices, the 5 attributes of a resilient grid, the performance curve framework for quantifying resilience, how to convert that into a dollar value, regulators can audit, and 3 case studies that show what this looks like in practice. We close with 14 frequently asked questions across 2 FAQ sections. This framework draws on DOE, NREL, PNNL, and NERC extreme weather methodology, and one binding new standard, NERC TPL-008-1. Under IEEE 1366, major event days are statistically excluded from reliability indices so that ordinary reliability can be compared fairly from one year to the next. The logic is sound, but the consequence is that the hurricane, the ice storm, and the cascading failure are exactly what the headline metric ignores. Reliability asks, under normal conditions, can the system keep the lights on? Resilience asks a different question. How far does the system fall and how fast does it recover? 3 forces are driving urgency around that second question. First, extreme weather is now a planning assumption. NERC TPL-008-1 now mandates extreme heat and cold transmission planning. Second, load is exploding. Data centers and AI campuses are driving approximately 25% more peak demand than planning assumptions assumed just a few years ago. Third, regulators want proof. Reproducible, auditable metrics are increasingly required before cost recovery is approved for hardening investments. The differences between reliability and resilience run deeper than scope. They reflect fundamentally different modeling frameworks. Reliability models the power system. Resilience also models the threat and its interaction with each component. Reliability works from a predefined contingency set, the NERC P0 through P7 categories. Resilience targets extreme, multi-component N-K events outside that set. Reliability checks discrete system states. Resilience is time-evolving. It tracks degradation and recovery as the event unfolds. Reliability criteria must be strictly met. Resilience accepts controlled degradation as a legitimate outcome when the threat is severe enough. The blind spot that follows directly from this. Reliability excludes major event days under IEEE 1366. Resilience targets precisely those excluded days. The 2 frameworks address different questions about different operating regimes. A resilient grid is characterized by 5 attributes, the 5 Rs, grouped into a proactive set and a reactive set. The proactive set covers how a system anticipates, prepares for, and adapts to threats. Robustness is the ability to withstand an event with little performance loss. Hardened lines, flood-walled substations. Redundancy is spare capacity and backup paths. Looped feeders, dual feeds, and reserve generation. Resourcefulness is the ability to adapt under crisis. Dynamic reconfiguration, distributed energy resource dispatch, and microgrid operation. The reactive set covers how a system responds and recovers once the event is underway. Response is the ability to mobilize fast, automatic load shedding, controlled islanding, and crew pre-staging. Recovery is the ability to restore quickly and learn, self-healing automation, and prioritized reconnection sequencing. Together, these 5 attributes define what it means to be resilient. And each points to different engineering investments. Quantifying resilience requires tracking system performance through an event. The performance measure can be load served, customers with power, or critical facilities energized. The key is that it is tracked continuously through the event, not just before and after. The resilience triangle is the simplest model. Performance drops at the moment of impact, then recovers linearly back to normal. The triangular area between the pre-event level and the recovery curve is the resilience penalty. Smaller is better. It collapses the entire event into a single drop and recover shape, which makes it a good first cut for comparison across events or investments. The resilience trapezoid is more powerful. It separates the event into 3 distinct phases: disturbance, degraded plateau, and restoration. Each phase points to a different intervention. Robustness improvements flatten phase 1, reducing how far the system falls at impact. Logistics and crew positioning shorten phase 2, reducing the time the system stays degraded. Automation accelerates phase 3, speeding the restoration back to normal. When real utility data is used, outage and restoration actually overlap in time, and the trapezoid generalizes to cumulative outage and restore curves built from time-stamped outage management system records. The choice of metric depends on the question being asked and the system being measured. Planning metrics are forward-looking and probabilistic. Operational metrics need to be fast and scenario-specific. The right tool differs between the two. Transmission and distribution face different dominant threats. Cascading N-K events are the primary concern at the transmission level. Localized feeder-level weather damage dominates at distribution. Grid metrics and community metrics are not the same. Community resilience adds dimensions the grid indices miss: microgrid islanding success rate, critical facility continuity, and socioeconomic exposure, and the choice between performance metrics, consequence metrics, and non-performance metrics matters. Load loss is a performance measure. Downstream economic cost is a consequence measure. Inherent hardening attributes are non-performance measures. They answer different questions and support different decisions. Finally, local scores rarely aggregate cleanly to system-wide scores. Networks behave non-linearly. The performance curve framework converts naturally into a benefit-cost case a regulator can reproduce and audit. The process follows 4 steps. First, calculate the curve area, expressed in avoided customer minutes or energy not served. Second, multiply by the value of lost load, expressed in dollars per megawatt hour by sector interruption cost. Third, the result is avoided outage cost, the core resilience value currency. Fourth, that number supports a reproducible, auditable benefit cost case. 4 valuation methods support different contexts: probabilistic risk assessment, cost-benefit analysis, resilience-adjusted resource adequacy, and macroeconomic impact studies, all connecting back to the same performance curve foundation. 3 case studies show what this framework produces in practice. The first is a hardening rate case for a coastal distribution utility. The challenge was building a regulator-auditable justification for a system hardening program. The resilience framework produced a reproducible benefit cost exhibit, avoided customer hours per program dollar, that served as the evidentiary foundation for the rate case. The second is a large load interconnection study for a hyperscale data center developer. High-impact, low-probability performance requirements needed to be translated into infrastructure sizing decisions. The resilience framework quantified the performance case and right-sized the on-site generation, storage, and dual-feed configuration against defined uptime criteria. The third is a community microgrid scorecard for a municipality managing a cluster of critical facilities. The goal was a defensible, communicable measure of microgrid value. The framework produced a scorecard expressing microgrid performance in critical facility hours kept alive, a metric legible to elected officials, emergency managers, and regulators alike. Resilience analysis requires data and faces real practical constraints. The data required includes time-stamped geolocated outage and restoration records, hazard data covering weather, flood, and fire, asset and exposure information, and a clean outage management system feed. In practice, inconsistent outage reporting, proprietary data sensitivity, and the statistical rarity of the largest events are the binding constraints that make this harder than it looks on paper. On the standards side, the landscape is converging. NERC TPL-008-1 mandates extreme heat and cold transmission planning, making resilience analysis a compliance obligation, not just a best practice. Recurring FERC and NERC post-event reviews are codifying performance expectations. DOE, NREL, and PNNL frameworks, including the RAPT tool and the Grid Deployment Office Metrics framework, are establishing reproducible methodologies across the industry. Here are answers to the first 7 frequently asked questions about power system resilience metrics. What is the difference between reliability and resilience? Reliability is about avoiding interruptions under normal conditions against a defined contingency list. Resilience is about surviving and recovering from rare, severe events that overwhelm that list. Why don't SAIDI and SAIFI already capture resilience? IEEE 1366 statistically excludes major event days so that ordinary reliability compares fairly year to year, filtering out exactly the days resilience metrics are designed to target. What is a high-impact, low-probability event? A rare but severe disturbance, hurricane, ice storm, heat dome, wildfire, cyber-physical attack, or cascading N-K failure that falls outside the conventional contingency set. What are the core attributes of a resilient system? The 5 R's: robustness, redundancy, resourcefulness, response, and recovery, mapped onto an anticipate, prepare, adapt, and withstand, respond, recover life cycle. What is the resilience triangle? A model where performance drops at impact and recovers linearly to normal. The triangular area of lost performance is the resilience penalty. Smaller is better. How is the resilience trapezoid an improvement? It separates the event into 3 phases: disturbance, degraded plateau, and restoration, and each phase points to a different intervention: robustness, logistics, or automation. Can resilience be measured from real utility data? Yes. Because actual outage and restoration overlap in time, the trapezoid generalizes to cumulative outage and restore curves built from time-stamped outage management system records. Here are answers to questions 8 through 14. How do you turn a resilience metric into a dollar value? Convert the performance curve area into avoided customer minutes or energy not supplied, then multiply by the value of lost load to produce avoided outage cost. Fragility curves or statistical outage rate curves, which should you use? Both, ideally. Fragility curves evaluate hardening on a specific asset. Outage rate curves capture the system's real combined response from historical data. They answer different questions and are most powerful used together. Does any standard require resilience analysis now? Increasingly, yes. NERC TPL-008-1 requires extreme heat and cold transmission planning, and recurring FERC and NERC post-event reviews are codifying performance expectations across the industry. How is community resilience measured differently from grid resilience? Community metrics add dimensions that grid indices miss: microgrid islanding success rate, critical facility continuity, and socioeconomic exposure factors. Why do data centers and large loads care about resilience metrics? Uptime requirements translate directly into resilience acceptance criteria, letting a developer right-size on-site generation, storage, and redundant feeds against a defined performance standard. What data is needed to get started? Time-stamped geolocated outage and restoration records paired with hazard data and asset and exposure information, ideally from a clean outage management system feed. How does Keentel protect client confidentiality in published work? Every public deliverable is written in Keentel's own voice, with client names, locations, and proprietary data removed or generalized. Here's a blind spot most utilities don't talk about. SAIDI and SAIFI, the standard reliability numbers, actually exclude major event days by design. The hurricane, the ice storm, the cascading failure, none of it enters the score. That's exactly what resilience metrics measure instead: how far the grid falls in a severe event and how fast it recovers. With NERC's new extreme weather standard now mandatory, this isn't optional anymore. If your utility needs resilience metrics or a defensible rate case exhibit, Keentel Engineering can help. Visit keentelengineering.com or call 813-389-7871.